Okay, in this chapter, we'll define a quantity called momentum, and we'll see that on a closed system, if there is no external force acting on it, then momentum will be conserved. Okay, so let me show you a couple of examples. Okay, so you guys have all played pool, and what will show you is the following. Okay, so he'll hit the cue ball, and momentum is mass times velocity. The cue ball will have a momentum. He'll give the system a momentum. This will collide with this rack, and all these balls will scatter. And through that entire thing, the momentum will be conserved. That is, the total momentum of the system will be this constant. Okay, initially, only this guy has momentum, and then after the collision, all those balls have momentum, and the sum of all those momentum will equal the momentum of the cue ball. Okay? Until at what time?
Until friction adds up to overcome the
So,
moving system.
so we're ignoring friction until one of the ball hits the bank. Then you have an external force. Okay. So all this happens very fast. So let me show you.
Look at that. Is that not the most pretty rack you've seen? That right there is how you're supposed to rack the ball.
Okay. So after the collision, okay, till one of the balls hits the bank, the momentum of all those broken balls was equal to the initial momentum of the cue ball. Okay, so so that was sort of a neat statement. I mean, that was a complicated explosion, and we could say something about it. We could say that the momentum of all those balls was equal to the initial momentum of the cue ball. Okay, so let me show you. So here's a okay, and we can change the mass and velocities as you needed. Okay, so we'll get these guys going. This guy will have a momentum in this direction. This guy will have a momentum in this direction, and we'll say the values. We won't do the velocity vector. Okay, we'll just do momentum. So this guy has an initial momentum of 0.5 kg meters per second square. This guy has a momentum of minus 0.75 kg per meter square. The total momentum is 0.5 minus 0.75, which is minus 0.25. And after they collide, the momentum will be minus 2.25. Okay? All right, let me. Okay, we won't have reflecting borders. Okay, so again, minus 0.25. Come back, I guess. Okay, so initial momentum was minus 0.25. There's minus 0.63 plus 0.38, which is minus 0.25. Okay, and we can change the masses any which way you want, and momentum values reflecting. Okay, so now the initial momentum is 1.9 minus 0.75, which is plus 1.15. You guys understanding this? Okay, So the momentum after the collision should be 1.15. Okay. 1.77 minus 1.16. Okay, so within rounding errors. Yeah. So again, the point of this is, in physics we study complicated motions and stuff like that, and we want to be able to say some quantity that's conserved. Okay, so when you study collisions, it's momentum is a very important concept. It turns out that momentum is conserved when there's no external forces acting on the system. And so that's what we're studying. Okay, so momentum is what we'll study. And again, like I said, it's an important concept when you study collisions. Okay, so, and again, we're studying linear momentum. In a later chapter, we'll study angular momentum. Okay. So linear momentum is what we're studying, and then collisions and impulses are two phenomena where this concept will be important. So we'll look at conservation of linear momentum, momentum in collisions, and so on. Okay. So momentum is denoted by P. It's a vector quantity, and let me define it right away. So it's the mass of an object times its velocity. Okay. So it's a vector quantity. We define a conserved quantity, linear momentum, which will put an additional constraint on how a system evolves in time. Okay, so if something has to be conserved, then that puts a constraint on how the system can evolve. Okay, so conservation of momentum is useful for understanding collisions. Okay. The quantity momentum is just as powerful, important, and useful as energy. Okay. So in this illustration, this guy has this initial momentum, and this guy has this initial momentum, and when they collide somewhere here, this guy flies off there, and this guy flies off here. Okay, and if there's no external forces acting on the system, the initial momentum, the sum of these two, must equal the final momentum. Okay, so the total initial momentum is this plus that, which is this, and you see the total final momentum, which is that plus that, is the same. The total momentum is conserved. Okay. So here's another situation where it's important. Often we encounter situations where the applied force, so the bat is applying a force on this ball. This force that the bat is applying is very short-lived. For a baseball, it may be about 50 milliseconds. And in addition, the force is not constant. So you'll see that the force as a function of time will be something like that. Okay. So we encounter situations where the applied force varies with time, as a function of time, and is non-zero for extremely short intervals. Okay. So the force that the bat exerts on the ball will, like I said, will be non-zero for about 50 milliseconds. Okay. So to analyze such situations, it's convenient to define linear momentum. So there's linear momentum denoted by P. Again, it's a vector quantity, and it's the mass of the object times the velocity of the object. Okay. What is Newton's second law? You guys remember? Okay. So you saw that in one of the previous chapters. This was Newton's second law. Okay. Well, actually, the correct form is this. Okay. This we'll see in a second when that one applies. Okay. So Newton's second law says force on a system is equal to rate of change of momentum of the system. Okay. The force on a particle. So let's see this. Net force equal to d by dt of momentum, which is mass times velocity. Now this is equal to, let's say, again, now in most situations this is not true, but let's say the mass was a function of time. Then this would be dm by dt times velocity plus m times dv by dt. What is dv by dt? And the acceleration. So this is equal to dm by dt of velocity plus mass times acceleration. And there's that fellow that we talk about. So this guy applies when this is 0. dm by dt is 0. So for instance, when you're driving your car, does the mass of your car change? It does change, but it's negligible. So this, in most of the situations you encounter, this can be dropped. And that's when this formula works. Can you think of a situation when this is comparable to that? When you cannot drop this? I'm sorry? Rocket ships, okay? So when you're flying a rocket, 90% of your mass is fuel. Okay, so for instance, the space shuttle would lose 90% of its mass in a few minutes. Then this guy is comparable to this guy. Okay? All right, so this is Newton's second law. That is an approximation when dm by dt is 0. Okay? So we'll consider situations where dm by dt is not negligible. Okay? All right, here are some momenta. Okay. The reason we are giving you this is, see, now that you know Newton's correct formula, dp by dt, think of this as change in momentum about, okay? Okay, so if an object has a large momentum and you want to stop it, the force you have to apply is that would, the change in momentum. The faster you stop it, the greater the force you have to apply. Okay? And the slower you stop it, greater this is, the smaller the force you need to apply. Okay, so here are some. An alpha particle is a helium nucleus. Uranium-238 will spit that out, and that's the momentum of the alpha particle. Here is a charging rhinoceros. See, its momentum is roughly the same as the momentum of a car moving on the highway. Okay. So you would roughly need the same force to stop both of them. Here's a supertanker. Its momentum is 5 orders of magnitude greater, 100,000 times greater. Okay, so stopping a supertanker is 100,000 times more difficult than stopping a car. Okay. Okay, so here's the idea of safety devices. Now that you know this formula. Okay, what is bad for your health? High accelerations are bad for your health. Okay. Okay, so your mass doesn't change. You can't change your mass in situation. Okay, so to have lower accelerations, you need lower forces acting on you, smaller forces. Okay, let's say you have a certain amount of momentum. Let's say you're moving at 80 miles an hour on the highway. If you get stopped fast, if delta t is small, then the forces on you will be large. You'll experience high accelerations. Not good for you. So what safety devices do is, if you have a certain momentum, if you're moving at 80 miles an hour, what are safety devices trying to do to you? They're trying to stop you over a longer period of time. Okay, so if the stopping time increases, the force acting on you is smaller, acceleration will be smaller. And that's what this guy does. Okay, instead of the steering wheel stopping you, let's say your car hits a wall or something like that, you keep going at 80 miles an hour and the steering wheel will stop you. That's not good. So if you deploy a airbag, now the airbag stops you over a longer period, the forces on you are smaller. Okay? And in addition, the airbag did another thing. What did it do? It applied, okay, so let's see this. Okay, I'm going to apply a force of 15 pounds. Did that hurt? No. 15 pounds. Did that hurt?
Yeah.
Okay. So the airbag, it's applying a smaller force over a larger area as well. Okay. So so there's two ways it reduces damage. Okay. Anyway, so you have to remember this. Okay. So again, you've seen this equation as well. Okay. If you're stopped over a larger distance, a greater distance, the acceleration you experience is smaller. The forces acting on you are smaller. Okay? Or equivalently, if you're stopped over a longer time period, the forces on you are smaller. Okay? All right. Now we'll talk about impulse approximation. Okay, so there'll be situations when one force is much larger than any other force acting on the system. So let's say, okay, so there's the force of gravity, the normal force, they're canceling each other. There's friction force between the ball and the tee. And when the club comes in contact with the ball, the force the club exerts this force is much larger than any of the other force. So when that force is in play, we can ignore all the other forces. Okay? And this is the impulse approximation. Okay. All right, so, and this force, the peak force, can be as large as 3,000 times the weight of the ball. Okay, so in golf at least. And in baseball too. Okay, so that's the impulse approximation. So this force we're going to study now, this force, which is a function of time. Okay, so if this is just when the club gets in contact with the ball and the force rises as the ball and the club are compressed, and there's the peak force, and the force has gone back to zero when the ball has left the club. Okay. Now here's another thing we're doing. Okay. In the previous chapter, one of the previous chapters, we learned how to handle forces that varied with position. Do you guys remember what this area was? We just did problems. What was this integral? That was work. Okay? In this chapter, you will learn. Now we're learning how to handle forces that change with time. And you learn that this area is called an impulse. Okay. Impulse is denoted either by I or J. What did work do? If you do work on an object, what does it do? Yeah, it changes the kinetic energy of the object. Okay? You learn what does impulse do? It will change the momentum of the object. Okay? So that's what you learn. Did you guys understand that? So forces that vary with spatial coordinates, that area is equal to work. When forces are varying with time, this area is called impulse, which is changing the momentum of the object. All right, so here's the situation we're considering. Okay, so you saw that Newton's second law is force is dp by dt. Okay, here's an equation. And what we'll do is we'll integrate both sides. Okay, so we will dp by dt and we'll integrate with respect to time. Okay, and I'm not writing vector notation. Okay, integral is an antiderivative, so this undoes that, initial to final. So this is P initial to final, and that's equal to this area. Okay, so you have this short-lived force, and the area under this curve is that, and that is equal to P final minus P initial. So P final minus P initial is equal to this area. This area is called an impulse. Okay, so the impulse acting on the object is the change in momentum of the object. Okay. So in the case of the golf ball, initial momentum was 0, the ball was at rest. And so the impulse imparted tells you the final velocity of the ball. Okay. So the difference between a professional golfer and, let's say, an amateur golfer is they're able to impart a much greater impulse off the tee, and the ball comes out with a greater velocity. Okay. So greater this area, well, more money you're making on the golf course. All right, so we will do an experiment like this in lab where you'll measure the force 500 times a second. So that'll be one of the best experiments you do in this lab. Okay. But oftentimes it's hard to measure this force in detail as a function of time. And most of the time we don't care to measure it, so we're happy to just know the average force. Okay. So the average force is calculated such that the area of this rectangle is equal to this area. Okay, so the average force and the time over which the force acts is maintained constant. Okay, so average force times time over which it's acting should equal this area. So the impulse is average force times the time over which the force acts. Okay. All right, so Newton's second law says net force acting on the object is dp by dt, rate of change of momentum of the particle or the system. The net force is the sum of internal forces plus external force. Let's say if these guys were charged, then if they were both positively charged, they would repel each other. Okay, those would be internal forces. Okay. But this guy would repel him and this guy would repel him, so their action and reaction, and they would add up to 0. So internal forces always add up to 0. So the net force acting on a system is just equal to the external force. And now if there's no external force acting on the system, if this is 0, dp by dt is 0. That means momentum is not changing. And that's what was happening on that pool table, okay? There was no external force acting on the system. If there's no external force acting on the system, the momentum before the collision is equal to the momentum after the collision. Okay? They're deflecting each other because of internal forces. So on a pool table, you might say, well, there's gravity, but the gravitational force was being canceled by the normal force. Okay, so there was no external force. So as long as there's no friction forces, momentum will be conserved on that pool table. Okay. So here's a very neat application of this formula, of this concept. Okay. So in a in a particle physics lab, in those colliders, they make these particles all the time. So here's a kaon, and it decays probably within a millionth of a second. You can look it up. Okay. So if this guy is produced at rest, what is his initial momentum?
0.
0. Very good. And this guy, he happens to decay into these two particles. This is a particle anti-particle pair. Okay, there's no external force on the system. The breakup is due to internal forces, so to speak. So what is the momentum of this guy going to be?
0.
0. Okay. So this guy, these masses are equal, so they have to go at the same speed and exactly in the opposite direction. Okay? So this momentum conservation implies that they cannot have different speeds, and in addition, this guy can't go there and this guy can't go here, like that. So among the infinite possibilities, this thing restricts to only a few. So it can still go in many directions, but they're exactly in the opposite direction and exactly the same speed. Okay, so that's what momentum conservation will tell you. All right, now we'll apply these ideas to collisions. Okay. And so in collisions, there's no external forces acting on the system, and most real life collisions happen so fast that even if there were external forces, they don't have enough time to change the momentum. Okay, so momentum will be conserved always. Now we'll classify collision based on whether kinetic energy is conserved. Okay. See, if kinetic energy is conserved, if final kinetic energy is equal to initial kinetic energy, then we call that collision an elastic collision. Okay. So on a pool table, the collisions are elastic, okay, to a certain degree. 98% of kinetic energy is conserved. In this room, all these air molecules are colliding billions of times a second. And those are all elastic collisions. Okay. So in all these collisions, momentum is always conserved. In all these collisions that are happening in the gas molecules, kinetic energy is also conserved. If kinetic energy is not conserved, that is, if final kinetic energy is less than initial kinetic energy, then it's an inelastic collision. Can you think of an example of what is an inelastic collision? When two cars collide, the final kinetic energy is always less than initial kinetic energy. What happens to the kinetic energy? goes into crumpling the car, sound, heat, and all that. Okay? So nowadays, a lot of cars, modern cars, have a crumple zone. Okay, the engine will drop and it'll have a crumple zone. So a lot of the energy of the collision is taken into that. So there's less energy to go damage you. Okay? So final kinetic energy is less than initial kinetic energy. That's called an inelastic collision. If final kinetic energy is 0, then that's a perfectly inelastic collision. Okay, so let's say you take two pizza doughs, balls, and you shoot them at each other, they'll stick and come to rest. That would be a perfectly inelastic collision. Okay? If kinetic energy, final kinetic energy is greater than initial kinetic energy, that's an explosion. Okay? So how did energy increase? Well, some kind of chemical energy or something like that was converted to kinetic energy in an explosion. Okay. All right, so in all collisions, momentum is conserved. Okay. So that is always there. So here is two balls colliding before the collision and after the collision. If they stick together, this is an inelastic collision. Okay. And if they stick together, then their final velocity will be, you can precisely calculate this final velocity because this momentum has got to equal this momentum. Okay? And so this is an inelastic collision in one dimension, meaning they're going in one straight line, okay, in one line. So here is the initial momentum. Okay, so we know that momentum must be conserved, okay, in a collision. So here is the initial momentum, momentum of particle 1 plus momentum of particle 2, and here is the final momentum. And so the final velocity is the initial momentum divided by the total mass. Is the initial momentum divided by m1 plus m2. Okay, so you can precisely calculate the velocity. Now, if it's an elastic collision, what does that mean? What does elastic collision mean?
All energy is perfectly transferred
So-
between objects.
Momentum is conserved, and now kinetic energy is also conserved. Okay, so now you have two conditions. You got to satisfy two conditions. Okay, so it's a more restrictive collision. Okay. So here's initial momentum, final momentum, initial kinetic energy, and final kinetic energy. And now if this thing is happening in one dimension, you can manipulate these two equations, and here's a fairly neat thing you can see. Say, okay, so this equation is just the momentum conservation again. Initial momentum equal to final momentum. But here's the neat thing you can say. Here's the relative velocity, v1 minus v2. What that means is if this guy is going at 10 meters per second and this guy is going at 5 meters per second, what is their relative velocity? 15 meters per second. Okay? So you're going at him at 15 meters per second. Okay? The final relative velocity is negative of the initial relative velocity. Okay? After you collide, you'll be moving away at 15 meters per second. Okay? So that's what that equation is saying. Okay? And I can, let me show that to you. Okay, so we'll do velocity values. There you go. Okay, so this guy is going at 1 meters per second, and this guy is going at 0.5 meters per second. So this guy is approaching him at 1.5 meters per second. Okay? And after the collision, he must move away from the guy at 1.5 meters per second. relative velocity. Okay, oops, what happened? Okay, so again, 1 meter per second, 1.5 meters per second is the relative velocity. And this guy is moving away at 1.25 meters per second, 0.25 meters per second. So he's moving away at 1.5 meters per second. Okay? And you can change the mass and okay, so again, for different masses, here's relative velocity of 1.5 meters per second, and since this guy was heavier, this guy flies off. 1.13 plus 0.37, again he's moving away at 1.5 meters per second. Okay. All right, so that's the neat thing we could say. All right. We'll do this slide and then we'll stop. Yeah. We have too many slides, okay? 2D collisions. So now we'll play pool. Okay, so we'll collide in 2 dimensions. So again, here's a vector. This is a vector equation. Okay, so if the collision is happening in two dimensions, p1x equal to pfx, p1 piy equal to pfy. Okay, that's all that means. Now you have yet the x component of the momentum is conserved and the y component of the momentum is conserved. Okay. So when this guy collides with him, this guy flies off there, this guy flies off there. There's the x component of the momenta, which the sum of these guys will have to equal this guy, mass times all that. And the y component of the momenta have to cancel each other. Okay? So here's the x component of the momentum equal to the final x component of the momentum. Initial y component of the momentum is equal to initial final y component of the momentum. And if it's an elastic collision, then kinetic energy is also conserved. And this happens in the pool table. Okay, so these 3 conditions must be satisfied. Okay, so here's a neat thing. In a pool table, the cue ball and the object ball, all the object balls have the same masses. So when the masses are the same and it's an elastic collision, then you can show that after collision, this angle, the angle between these 2 guys, is always, do you know what it is? Have you played pool? Who has played pool? Okay, do you know what this angle is? You do, because you play it, the game. It's 90 degrees. See, your brain knows it.
You're saying like the
So after these, this is the cue ball, this is the object ball. They collide, and these guys will go off at 90 degrees. See, you guys intuitively know physics without knowing that you know it. Okay, so let me show this to you. Yeah, do you play pool? No? All right. I mean, you look surprised. Okay, so let's 2D. Okay, so we have to have masses equal. All right, and velocity, no reflecting border, elastic collision, momentum diagrams. one of the velocities has to be 0. How do I make velocity 0?
If you drag the V into the ball.
Okay. Okay, you'll just have to trust me on it. So. Okay, so it'll always go at 50, at 90 degrees. All right, so that's true. So you guys want to make money in pool halls? So I'll show you how to cheat. Yeah. What you do is you have a cue ball that is either heavier or lighter. So when you're shooting, you play with the normal ball. And the pool shark, when the pool shark is shooting, you give him that ball. And he'll miss all his shots. Of course, he'll figure it out pretty soon, he or she. Okay? All right, guys.